way a database is structured determines how easily it can be used for a particular function. In this video, we'll explore the differences between schemas used in transactional and analytical databases. We'll also explore how data is transformed from a transactional database to an analytical one. Our transactional database will follow a third normal form schema, whereas our analytical database will follow a star schema. A star schema is often used in data warehouses. We'll use these databases to answer questions that a business might want to know the answers to, and look at how queries to answer these questions would work with each database. We'll explore these concepts by looking at the data from a fictional bank called BurstBank. In particular, we'll explore one of their products, credit cards. The bank has data on customers, those customers' credit card accounts, and the transactions customers make to pay the balance on their accounts. BurstBank stores and organizes this information in either a transactional or analytical database, depending on how it will be used. Any transactions a customer makes are recorded in BurstBank's transactional database. This database needs to be able to reliably answer questions like, did customer A's payment go through successfully? Or, what is customer B's balance? So, this data must be used to answer questions like, which age group is at the highest risk of defaulting on their payments? Or, year over year, is the percent of customers making minimum payments increasing, decreasing, or staying the same? If we compare the questions we need to answer with each type of database, we can see that the granularity is different. Transactional databases answer questions at the level of one customer, whereas analytical databases are used to answer business-level questions with aggregated data. BurstBank captures all of the credit card data in its transactional system, the third normal form schema. First, account information for a customer's credit card account is stored in the accounts table. This includes information such as account number and the date the account was opened. Customer information is stored across several tables because it is normalized to reduce redundancy. The customer information table includes customer name, date of birth, and estimated income. It is connected to the accounts table with the customer key. It is also connected to the customer location and phone tables with the customer key. Information about the credit card associated with an account, such as the credit card number, is stored in a table that is connected to the accounts table with the account number. Finally, each time a customer completes a transaction, the information from that transaction, such as the amount and remaining balance, is recorded in the transaction table. This table is connected to the accounts table with an account number. Now that we have our transactional database schema, let's use this database to help us answer a few of the questions we asked earlier. One of our customer-level questions was, did customer A's payment go through successfully? A customer service representative might be in charge of answering this question, which they could do easily if they had the customer's account number, because they could use it to look up the payments made by that customer to find out the last payment that was made. What about the business level questions, though? One of our questions was, which age group is at the highest risk of defaulting on their payments? To answer this question from the third normal form database, we'd have to do a complex query to combine the results of many different customers. This is not efficient, and instead it may be easier to store the data used to answer this type of question in an analytical database. Then, the complex transformations needed to make the data useful for business-level queries only need to be done once, instead of each time a query is run. Let's look at how this transformation would work. We'll take our third normal form database and turn it into an analytical database that follows a star schema. To do this, we'll aggregate some data and split other data into finer categories that data analysts might use to answer business-level questions. Remember, star schemas consist of a central fact table that is connected to denormalized dimension tables. We'll start by turning the customer location table into a dimension table. We don't need information on individual customers in our analytical database, but business analysts might be interested in customer groups. So, we will use customer age and estimated income to create categories for age ranges and income levels, and then we'll store them in a customer dimension category. From the account table, we'll create an account dimension and store credit card information there too. Finally, from the transaction table, we'd like date to become its own dimension, but we'll split it more finely than we'd need to in the transactional database. Other data from the transaction table will be aggregated into the payments fact table, including payments collected, principal collected, and percentage minimum payments. Since we don't have information on individual customers in this table, it would not be possible for us to answer customer-level questions. However, answering the question, which age group is at the highest risk of defaulting on their payments, would be easier. To do this, we'd simply need to run a query that joins the customer category and payments tables. Even though both of these databases were created from the same customer data, they serve different purposes. Data structure matters because it influences what you can do with the data. Taking transaction data and storing it in a data warehouse can allow you to organize data according to the type of questions you want to use it for. This greatly increases query efficiency for business questions.